point of recursive functions, or recursion, they like to use the term relations. The whole thing about recursive relations is that you use previous terms. The previous answer builds the next. So what's better than talking about money, right? You make some money, the next month you're going to make some more money. That money will help make more money. And one of the secrets to capitalism is if you have money, you're going to have more money most of the time. You can lose it, but the more money you have, the easier it is to make more money. The less money you have, the harder it is to make more money. It's a recursive math function. So if you have a recursive relationship, let's say you have $100, and the next month you add 100, and then the next month you add 100. What kind of a sum are we going to have from month to month? We'll have 100, then we'll have 200, then we'll have 300. What kind of a series is that? 100, 200, 300, 400. That's arithmetic, right? You're adding so much each month. And so if you look at it from a mathematical recursive form, all you're doing to get the next one is you take the previous amount that you have and add that $100. That's arithmetic. So notice it's a of n is equal to a of n minus 1 plus b. And by the way, this is a degree what? 1, right? Okay, so next thing we could do is you could take that $100 and invest it. And that $100 is, you're going to invest it, and it's going to make some interest. Okay? Yes? So if you take that $100, and let's say you get 6% per year on that. That's a lot, but let's say you do. You get to multiply by 6.06 for if you're looking at this per month. No, it's a 1/12 of that, right? You get a 1/12 of that. And then do you remember with compounding interest, you take per month, and then the next month, you're going to get that amount that's a little bigger, and then the next month a little bigger. So what essentially you're doing is you're taking this original amount times 100, and then you're adding this interest, and you're doing it n times, right? And, this is definitely going to be geometric, a, r to the n. But what we're really thinking about is as we're taking the previous amount, a of n minus 1, and we're multiplying by the same thing every time. Month 1, month 2, month 3, and that grows, and then it's something else. So, that shouldn't be 100, though. That's interest rate here. R times a of n minus 1, the previous amount. So this is geometric is a little different. There's nothing added to this. But what if you're doing both? And this was my argument in honors pre-calc is, in higher algebra, they always talk about growing money, but nobody gets, when they're 16, not very many people anyway, $500,000, and it gets to accrue over time. Not many people do that. I know some of you do, but not very many. And so what normally happens are people add an amount each time. And so this is the geometric series, or the recursive series that has a rate of your interest rate, but then you're adding each month. Then what's this one? Let's see, wait a minute. Oh, no, that's what I'm doing, adding b. So r of a n minus 1 plus b. So this is your investment per pay period. This is the way most people invest. This is how I invest. I put so much in a month, and it grows. So does all the rest. It grows. I didn't have that big chunk to drop. This would be the big chunk to drop. This is lump investment. And then this is just, an amount of money without any interest. So when we look at these, and you're pretty familiar with this, I'm not going to bore you with going through the derivation of these. The idea is you take your previous amount, and then you're going to increase it by some interest rate. Here they had 7.5 per pay period, or per year. Per annum is per year. This is per year. But then the pay periods, there's only 4 times a year that these are going to be compounded. So 4 times a year, you only get a fourth of that 7.5 each pay period. And so normally we look at this number as being what? When we say monthly, 12 is what that number usually is. So 1 plus 0.075 over 12 times how much you put in. And then the next month you do it again, but now you're going to be able to take that last total and then multiply that by 1.018. And then next year you'll be able to do that total by 1.108. Well, anyway, this just gets, all the way to the nth power times whatever you started with. And so this is the one we're familiar with for compounding interest. And what's cool about it, it's the A of n times some amount, some rate, A of n minus 1. And don't forget the rate is 1 plus the rate over the compounding periods we can call P for periods. That's what R is. This one, you're compounding it, and your money's growing and growing and growing and growing. And what they do here is they change this. Instead of using the recursive formula, they use this one. And this is if you're adding to a savings account, the previous grows geometrically. So that geometric growth we can change into the geometric sum, R of n minus 1 over R minus 1. And so that's why this formula plus this one yields this. This is how we would invest per period. Invest per period. This is the way I like to invest. Put in so much a month and watch it grow. My favorite, though, is this one, is paying off debts. You do borrow from time to time a bunch of money, and your per month is going to be minus that from the total. And what if the amount that you put in is less than the interest rate of your bank? What happens to the amount you owe? Keeps going up, 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 up. So this number here has to be greater than the interest rate. Would they like it if it equaled? Why? You'd pay forever, okay? But this has to be greater than this amount that you pay, we'll call P here. That pay has to be greater than 1 plus your rate over the pay periods that you do, in this case 12. So you got to make sure that's bigger. And once it's bigger, then you go through the recursive formula. So I think you're okay with that. Can I give you some money advice? I'll give you some money advice. It'll save you someday. If you are thinking about buying a home someday, and all of you will, I would guess, do what I did. The smartest thing I ever did was we made our house payments, and it was a 30-year loan. That's what we could afford right away. But it was like a year after we did that, we just added $100 to every house payment. And what that did is when we calculated it, the first year we were paying like, maybe $30 off the principal. And we pay like $1,100, or I think it was $1,000 house payment. And it was only like $30 that was coming off the principal the first year. And so we weren't knocking that down very much. But by adding 100, it was like 5 months of house payments in the beginning. And so if you can just, on $100, you can save that by, not eating out once a week and whatever. And you can change. We changed it from a 30-year to, I think it was 21 years or 20 years, just by doing that, adding 100, and huge help. All right, so what you're going to do is write down the closed form for each of these. And so this one here is, of course, just going to be your geometric. So the geometric rate we have is going to be 100. And then it's 100 times this one, 100 times that one. And so maybe what you would want to do, here's what I would do. I would start it out, make a list. A0 is 0. What's A1 going to be? Still 0. So what's A2 going to be? Yeah, so this is pretty tough. But what if A1 is 500? A2 is going to be 500 times 10. That'll be 5,000, right? What will the next one be? 50,000. Okay, and so this is just going to be 5 times 10 to the 2, 5 times 10 to the 3, 5 times 10 to the 4. So this will be, A of n will be 5 times 10 to the what? 10 plus 1. And is that closed? Did you see any previous terms in there? Or next terms? No. So now it's closed, degree 0. So you just go ahead and work those. Those are some pretty nice problems with some applications. There's really only 3 different formulas that you have. You have this one where you're subtracting an amount from a geometric growth. Here's where you're adding an amount to a geometric growth. And then the other one was just you are multiplying by a geometric growth. So you're not adding or subtracting. You're just taking that lump sum and growing it. And this was kind of a nice chart, I thought, for these. On this side is the recursion part. It has these main ideas. These are the recursions. This is like random. These are like a general form. This is not really one of them. And then you have the actual closed forms here.